Hello, everyone. Welcome back to, I almost said historical. This is Physical Geology 1403. Today is Lecture 3, and we are going to talk about igneous rocks and intrusive activity. Fun, 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 fun. Okay, but before we get into that, as usual, I'm going to open the floor to any questions you may have. Anything about the last two lectures? You're 2 lectures deep, 1/8 of the way through the course. Pretty straightforward. Feel like you're catching on? How are we doing with Lab 1? Have you had some time to look at that, think about that? Are you feeling confident? You feeling not confident? Not feeling confident? Okay, we will have time after class today to talk about what's making you not feel confident. I will answer those questions. I want you to feel like you know what's going on with this lab because it'll daisy chain into the other labs, okay? The format is the same while the content is different, okay? All right. Any questions of any type? Any scientific fun facts that we want to share with the crowd today? I got one. The Nancy Grace Roman telescope, which is the largest, most powerful telescope humanity has ever built, is getting launched on the 30th. Have you guys heard about this? No. Have you heard about the Hubble telescope? Nope. All right. The Hubble's been up there for a while. A lot of people have heard about that. It's parked in orbit, and it just looks out at the stars. Well, being parked in orbit is definitely better than being a telescope on the planet. Why? A telescope on the planet has to look through the atmosphere. Difficult. Telescope in orbit doesn't have to look through the atmosphere, but it does have to look past a bunch of other stuff. It has to navigate around orbital debris. It has to deal with looking out at the moon. It has to deal with the brightness of the sun at certain times of the year and wherever it's pointed. The Nancy Grace Roman telescope is not only an extremely powerful, the most powerful telescope, it's also going to fly 1 million miles away. They're going to park it 1 million miles from Earth, and it's going to sit out there taking pictures of deep space. We will get the most advanced pictures of galaxies and nebulae and all that stuff. The best pictures we've ever gotten, and I'm so excited. And that launches on the 30th. Bring it on. Okay. Also, I've had some dealings with NASA in the past. And ongoing, where various members of certain teams will talk to me about their projects, and I'll talk to them about projects. We'll exchange ideas. And one of the results of that was I got an email a few months ago saying, hey, the team that's putting together the Nancy Grace Roman telescope is going to attach a flash drive to it. They're going to put a little flash drive inside of it with the names of, what they say, 100,000 people. Do you want us to put any names on there? I was like, yeah. So I put my name, my wife's name, and my 3 kids' names on there, and they're going to go 1 million miles out to space on that flash drive, which is pretty cool. Pretty cool. Okay. Class announcements. This is week 2. You have Lab 1. You are getting Lab 2 on Thursday. Lab 1 should be turned in, ideally, before you start working on Lab 2, because if you don't, you won't really know what you're talking about with Lab 2. So make sure you get them in sequential order. Your first exam is not for a couple more weeks, so don't worry about that quite yet, except for taking good notes. Your notes are going to be your best friend on the exams. And as always, please ask questions here in class or over the internet. Send me an email, whatever, okay? Let's make sure that you are feeling confident about how this class works and what's expected of you, okay? Let's see. I think that's all I've got as far as announcements go. Any questions about any of that? No? All righty. Shall we jump in? Yeah? You know what? Let's not jump in quite yet. How many of you guys have ever touched a meteorite? You want to hold another one?
Have you ever been to that one museum and it has everything about space kind of? You can see the whole room.
Where is it? In Houston? I have not. I haven't spent too much time in Houston. We have a meteor crater here in town. Did you know that? The Odessa Meteor Crater. It's just outside of town. You go down the highway, take exit 108. There's a sign for it. I'm on the County Meteor Crater Advisory Board. Right now we're collecting a bunch of money to enhance the facility. Right now there's a little museum, but you go there and it's not terribly impressive. We want to make it impressive because it's one of the largest meteor craters in the United States, and it's right outside of our town, and there are almost like no other towns with a meteor crater right outside of it. This is a huge thing. Astronomers from all over the world come to look at our meteor crater, and the community knows nothing about it. So we're trying to enhance it and make a facility that people in Odessa can be proud of. But this is a piece of that meteor. It was about the size of a small SUV when it landed 64,500 years ago, and it made a gigantic crater. It doesn't take much because these things are traveling at about 10,000 miles an hour when they pass through the atmosphere. Okay? So one about the size of a shoebox would make a crater the size of this building. Okay? So this is a piece of it, and it's got that nice flat shiny surface because over Christmas break I sliced it in half. This is an extremely dense iron nickel alloy with a few other trace elements like uranium and palladium and things like that. But because it is super dense, there's no air in this thing. It's all super dense metal. It took me 3 hours to cut through this, and I went through 2 diamond saw blades. Yeah. So I'll pass this around. This thing was flying through space for billions of years before it landed here, 64,500 years ago. I know, it's heavy, huh? Heavier than you think it should be because it's complete metal, solid metal. Like when you look at, I don't know, something made out of metal. Why do I have nothing made out of metal around me? It's all plastic. I guess like a key or something, like this keychain right here. It looks solid, but there's still some component of gases in there, predominantly oxygen, because it was manufactured in an oxygen atmosphere like here on Earth, right? Most metals that we make here are. That's not, because it came from space where there is no atmosphere. It's where all the metals came together. It's pretty cool. Pretty cool. All right. While that's getting passed around, we can go ahead and get started. All right. So when I say volcano, what do you guys think about? Lava. Bingo. Let's hope that here. Oh no! Already off to a rough start. Hold on. I got to fix the speakers. It's playing through the laptop. I want it to play through the projector so it absolutely deafens you guys. What's the point if it doesn't? All right. Hold, please. Okay. There we go. That's the sound of a drone, by the way. All right. What are we seeing here? Describe it. Use words. I can't read thoughts. Huh? Magma is not technically wrong, but verbally it is. What's the word we have for magma on the surface? We talked about this last time. It's lava. Lava and magma are the same thing, but lava is what we call it at the surface. Magma is underground, okay? But yeah, what's coming off of that lava? Is it smoke? What is smoke? Huh? Say it louder. Steam is a big part of this, but the overall what we're seeing are gases. Some composition of gases coming off of this lava, okay? So we look at this, we're like, oh, that's so cool, or oh, it's so dangerous, or oh, it's so scary. However you're looking at it, right, there is science behind why it's happening, what it's made out of, and every process, okay? That's what we're going to start talking about today. Today and Thursday is all about that. That's called the igneous process. And no, we don't need to watch it again. Okay, so let's start off by talking about magma. Magma is melted rock. Okay? Why does rock get melted? What did we learn about the interior of the Earth last time? What state of matter, what state is the crust in? Solid, liquid, or gas? The crust. Solid. Thank you. Otherwise, we'd be in trouble, right? Next, we have the outer mantle. Solid, liquid, or gas? Solid. Yeah. Remember we learned it's hot enough that it wants to be melted, but it's under too much pressure to do so. Okay? Inner mantle. Solid, liquid, or inner mantle. Solid, liquid, or gas? Still solid, but squishy because it's getting closer to that boundary where it is so hot that regardless of temperature, it can be melted. Outer core. Yeah, that's the liquid one. Okay, so hot, yes, it is melted. Interestingly enough, the composition of the outer core, do you remember what it is? It's an iron-nickel alloy. What did we just pass around the room that has an iron-nickel alloy? The meteorite. Where's the meteorite, by the way? Great. These meteorites that land on Earth have almost the same composition of the inside of our planet. What does that mean? Implications. It's cool. There are some meteorites that we have captured in space or that have landed here on Earth that we have positively identified as probably coming from the inside of a past planet. One that got ripped apart, destroyed somehow, and the chunks are just flying around as asteroids now. Cool. Okay, I'll take that. All right. So as there is mantle material that is approaching the outer core is heating it so much that it does, in fact, enter a superheated, melted state. Now, what happens? What do we know happens to things when they heat up? Huh? Yes, they melt. They expand. Yes. This is the principle behind a lava lamp. As you heat things up, the volume increases, but the mass stays the same. I'm not adding mass. I'm only adding energy. By adding energy, I'm making those molecules in my material vibrate faster and faster and faster. As they vibrate faster and faster and faster, they are less willing to be as compact and joined together. Bonds start to break down. As the bonds break down, the molecules separate away from each other, and so volume increases while mass stays constant. What does that do to my density? Volume goes up, mass stays the same, density goes down. Okay? As density goes down, all of a sudden I have a material that wants to float up amongst the rest of the material around it. This is how a lava lamp works, and this is exactly what happens in our mantle. The superheated stuff in the mantle closest to the outer core gets that melted state, increases that volume, becomes more buoyant, lower density, rises up. And where does it eventually stop? The crust. Okay? And that's where it comes out. It pools under the crust as magma and pops up as lava, right? That's what we'll call that. Now, there is a liquid component to this, there is a solid component to this, and there is a gas component to this. All right? So, what's happening here? Our solid bonds are breaking apart because there's just too much energy for them to maintain that solid grip on each other. That turns it into a liquid. What happens when we take it even further? What happens when we superheat something enough? It becomes gas. Think about water. When water is in its lowest energy state, what is it in? What is its form? Ice. Thank you. It makes a crystal. It's a scientific fact. Crystals represent the lowest energy state of anything in nature. Okay? They have the lowest energy. You put energy into them, all of a sudden they start doing different things. But they have almost zero net energy. They are the lowest energy state that we know of, that I know of anyway. Okay? So, you add energy to this, they start mixing around and moving. That's when you get a liquid. What happens when we take our water, liquid water, and add even more heat to it? Steam. It becomes a gas. Zinging around so fast, doesn't want to bond with itself. The only time that it will ever actually condense is when it encounters a surface that absorbs its energy, right? Great. Now, as my magma is cooling down, what are the first things that form? You remember what we talked about this last week. What are the first bonds that form in that magma? There's one of something and four of another. If in your notes, it's perfectly appropriate to go look at your notes. What are the first bonds to form in the magma as it's cooling down? Yeah, I also wrote it on the slide. Thank you. Silicon tetrahedrons. Okay? One silicon, four oxygens. Covalent bond. You remember this? Okay. They are the ones that form first, and so they form the structure, the backbone of the silicate minerals that come after that. Remember, a silicate mineral is defined as one that is being built around the silicon tetrahedron. So all of the minerals that are going to come out of this, at least for a while, are going to be silicate minerals. All right? Okay. In these magmas and lavas that are cooling off, first of all, which one do you think cools faster, magma or lava? Why lava? I want to hear why lava first, and then I heard someone say magma, so I want to hear why magma. Give me the philosophy for why lava first.
Because it's exposed to air and all that.
Okay, so it's exposed to an environment that draws the energy way faster. Okay, why magma? It was an educated guess. Okay, she made a 50-50 guess. It is, in fact, lava that cools off faster for the exact same reasons that you mentioned. Okay? Not only do you have atmosphere, you also have water. How much of our planet is covered in water again? 71, about 71, okay? Melt all the glaciers, it would be about 72, right? Well, a little more than that, but you know what I'm saying. Okay, so what's the statistical likelihood that this magma is going to pop up under the ocean? Pretty high. So yeah, water is a big factor as well in pulling energy away from the system. Even just the not melted rock around it is pulling energy away from it. Okay? The closer it gets to the surface, the faster it cools off. The magmas that cool off the slowest tend to have larger crystals. Why is that? Doesn't have to do with compression. Here's an example that might help. If I told each of you that hidden in this room were 1,000 rubber ducks, and you had 10 minutes to gather as many as you could, you guys would probably get most of them. If I told you you had 10 seconds to get as many as you could, how many would you get? Zero confidence in yourself, right? I would get no rubber ducks, she's saying. No, you would get some, but definitely not nearly as many as if I gave you 10 minutes. Okay? The amount of time that these minerals have to form, these crystals have to pull more elements to themselves and continue making the bonds and growing themselves bigger is pivotal. Larger crystals only happen when you have more time to form them. Smaller crystals happen when cooling happens really quick. Does that make sense? Great. So we have names for this. When we see an igneous rock, which remember, igneous rocks are the ones made out of cooling magma and lava. When we have an igneous rock with large crystal sizes, we call that an intrusive igneous rock. Now, I want to be very clear here. This is not a description of composition. I'm not telling you what it's made out of. I'm telling you the environment it cooled in. What does intrusive mean? If I were to tell you this is an intrusive igneous rock, your immediate interpretation would be underground. Why? Because it cools slower there. Intrusive, large crystal sizes must have cooled off underground, where it was more insulated, where it lost heat slower. Extrusive, on the other hand, small crystal sizes. Where would that have cooled? On or near the surface. Bingo. Why? Small crystal sizes, not as much time to form crystals, less time before it cooled off. Okay, lost heat faster. We following this concept? Great. Good, 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 good. Now, leaving intrusive and extrusive behind, I'm going to tell you about compositions. Okay? Compositions are going to be your description of what the igneous rocks are made out of. Well, how can we tell what igneous rocks are made out of? That's why you learned minerals. Because remember, rocks are the chocolate chip cookies, minerals are the ingredients, right? So if you know your minerals, it'll be easier to figure out what your rock is made out of. Okay, so that's why everything in my class builds on itself, okay? So your first composition you need to know about is called felsic, okay? You might see some literature describe it as silicic. I prefer felsic, okay? Felsic. Break it down, if you like, into fel, so you can think feldspar, which is a light silicate, very common light silicate, and sic for silica, high silica content, okay? Then you have mafic. Think Ma, magnesium, fic, iron, suffix for iron, okay? So here we have felsic igneous rocks are made mostly out of light silicates, non-ferromagnesian silicates, your feldspars, your quartz, your muscovite micas, okay? Mafic igneous rocks are going to be made mostly out of your dark silicates, your ferromagnesian minerals, pyroxenes, amphiboles, olivines, biotite micas. Now, it's not going to be 100% one or the other. Most felsic rocks will have a little bit of dark silicates in them. Most mafic rocks will have a little bit of light silicates in them. Okay? Most of the continental crust is felsic in composition, generally speaking. Most of the oceanic crust is mafic in composition, generally speaking. Sorry, I know there's nowhere I can stand where I'm not in someone's way of taking notes. I apologize for that. Just wait for me to walk. Inevitably, I will keep walking, and then you'll be able to see what's behind me. Okay. Now, felsic and mafic are the majority of what you're going to be looking at in this class and what you will come across in nature. There are a few other compositions, though. Intermediate. What do you guys suppose that means? Yeah, intermediate. Huh? A lower than what? On what scale? If I were to say that I'm taking a piano class and I'm not beginner, but I'm also not advanced, what class would I be in? Intermediate. I would be in the intermediate class. So what do you suppose intermediate igneous composition means? What? In between what? Bingo! In between felsic and mafic, there you go. Generally around 50%. There's going to be like a 25 to 75% ratio a lot of the time, but you're going to see this is a pretty relatively even distribution between light and dark silicates. I'm going to call this an intermediate igneous rock. I'm going to show you examples of all of these, by the way. Okay? Have no fear. I will pass around some samples. All right. Then we have ultramafic. Ultramafic. Right? If mafic means high in iron and magnesium with a little bit of light silicates, what do you suppose ultramafic means? What do you suppose the word ultra means in general? Bigger, more, the most of something? Yes. So, ultramafic would therefore be the most dark silicates, the most ferromagnesian minerals. Ultramafic rocks have no light silicates. Okay? There, as a matter of fact, an example I already showed you last week was peridotite. I passed this one around. It's just olivine and pyroxene, two dark silicates, no light silicates present. Okay? That is ultramafic. The mantle is made out of ultramafic igneous rock. Okay? Now, this brings me back to silica. Remember, silicates are based around that silicon tetrahedron. All silicates have to have that core of silicon tetrahedron that the other, usually metal ions, attach themselves to. There is an inverse relationship between the amount of silica in a rock and the amount of iron and magnesium. Okay? What does that mean? An inverse relationship means that where one thing goes up, another thing goes down. You can only have 100% of a whole, right? If I said, I am 110% sure about something, that's not actually correct. I can only be 100% sure about something. If I said I had 120% of a cookie, that means nothing, unless I took some of Branson's cookie. I took 20% of Branson's cookie, and then I have 120% of cookies, right? But that would be rude, and I'm not going to do that to him because I like him, all right? So I can only have 100% of something, which means I'm going to have 20% of this and 80% of that, or 40-60, or 50-50, or whatever it is, okay? So for an inverse relationship to exist between silica and iron and magnesium, what I'm saying is if I have an igneous rock that is higher in iron and magnesium minerals, it's going to be lower in free silicons that can therefore go and make light silicates. And the opposite is also true. High in loose silicons that can result in light silicates, lower in iron and magnesium. Inverse relationship, like so. And that is about where you're going to get your composition swinging back and forth from, okay? Following the inverse relationship. Now, when I say low in silicon, there's still going to be a heck of a lot of it in there, because what are the two most common elements in the Earth's crust? No, that's the mantle. In the Earth's crust, though, what are the two most common elements? Together, they make more than 65% of all mass on the crust. Silicon and oxygen. Yep. Two of those 8. Remember there were those 8 elements that make up most of our Earth's crust? The two biggest ones, silicon and oxygen. So, with that much sitting around, inevitably there's going to be a lot of it in the rocks that form up here. Even when I say low silica content, I'm still talking like 40% of the mass of my rock is going to be silicon and oxygen in that silicon tetrahedron. Okay? When I say a high silicon content, that's more like 70%. Okay? Just keep that in perspective. I'm not saying that there is next to no silicons or oxygens. If that were true, I would not have silicates, because silicates require the presence of the silicon and oxygen, right? Okay. Now, how much of my, how much loose, what is this? Odd. How much silica is present in my lava and magma is going to dictate its physical characteristics as well, not just its chemistry. It's going to dictate how it moves. Okay? Who can tell me what viscosity is? What is viscosity? What does it mean for something to be viscous? Any ideas? You can feel free to read it off the slide if you want. It's resistance to flow. Thank you. What does that mean, though? Yes. How difficult is it for it to move? A liquid that has very low viscosity, water. Look at that. Very flowy, right? Except flowy is not a real word. We describe flowiness in science through something called viscosity. Very easy to flow. Low viscosity. What about something that has high viscosity, aka highly resistant to flow? Wait for it. Should we keep waiting? It's going to go. It'll go. Just hold the faith. This is corn syrup, by the way. This is what's in 80% of the food you eat. Your body can't process it because of, well, this. That's why it gets stored as fat, and we have a huge problem with weight gain in the United States because we put this stuff in everything because it's sweet and it's cheap to make because it comes from corn. It's going. You'll see a big bleh here in just a second. I'm going to angle it so it blets down right in the middle. So, highly viscous, very resistant to flow. The inverse relationship of iron and magnesium to silica in my rock, well, technically now in my melted rock, bless you, okay, is going to dictate, oh, you see it? You see the big doolop coming down now? It's going. It is flowing. The silica content is going to be the biggest factor for what controls the viscosity in magmas and lavas. Why? Well, as my lava or magma is cooling off, what's the first bond that forms? You see it? What's the first bond that forms? I gave you this one for free earlier. Who was paying attention? No, it's forming in lava. Well, can I drop it right down the middle? Oh, I touched the side. Look at that. All right. Silicon tetrahedrons, thank you. The more silicon I have in my melted rock, the more silicon tetrahedrons that form. The more silicon tetrahedrons that form, the more bound up in those bonds my melt is becoming. The more bonds that are forming, the harder it is for it to flow. The harder it is for it to flow, the more viscous it is. So, in my magmas and lavas that have the high ratio, where I have more silicon and less iron and magnesium, higher viscosity. In my lavas and magmas that have lower free silicons and higher iron and magnesium, lower viscosity, easier to flow. Let me show you. Here we have a pretty fast flowing mafic lava flow. It's probably in the way of the camera. Let me move that. Okay, did you guys see that? I'll play it again. If it'll let me. I'll leave this here so you guys can keep watching that flow down there. Can we play it again? You gonna let me play it again? Can I play it again? There we go. Look how fast that's going. It's pretty fast. Matter of fact, some mafic lava flows can flow like 20, 25 kilometers an hour. You better be on a bike. You ain't outrunning that unless you are like a long distance runner. Then you have felsic flows, like so, where you can barely even tell it's moving. They don't make it very far. And that's going to play into some of the stuff I'm going to tell you about here in a minute. Okay? Very slow moving. Now, I'm going to play another video here on the next slide, and it's pretty loud, so I'm going to say what I'm going to say now. I want you to listen to the audio of this, and you're going to hear wind. Try and tune out the wind. Listen to what's behind the wind. Okay, tell me what it sounds like. It sounds like breaking glass. Do we agree? Thank you. It does. Do you know why it sounds like breaking glass? If it looks like a duck, and it smells like a duck, and it quacks like a duck, and it poops like a duck, and it eats like a duck, and it does all the things like a duck, what must it be? It's a duck. Well, it's not. The duck isn't glass. It's a duck. But this is glass. Okay? This is glass. Why is there glass forming on this lava flow? What's happening here? We have lava that is clearly cooling off very quickly. Why? It's exposed to all that wind. You hear that wind. Even the atmosphere itself soaks up a lot of heat, but that wind is cooling it off very quickly at the surface. When I take lava and I cool it off super quick, I make a very particular type of igneous rock. You've probably heard of it. Obsidian. Volcanic glass. That's where it comes from. Extremely quickly cooled off lava. Okay? Okay. So you are literally hearing breaking glass on the outside of this flow because of how quickly it's cooling off. Okay? It's cooling, breaking, cooling, breaking, cooling, breaking. Over and over and over and over. It's way louder in person, believe me. This sounds like 1,000 dinner plates all shattering at the same time constantly. Okay? It's deafening. Okay. Any questions so far before I move on to the next section here? Yes?
Is that why it like, I don't know, like, I'm on TikTok a lot.
Okay.
But like, is that why like, in some videos like when they're like making glass or like forming them, they use like lava because it quickens it faster?
So the lava is actually the melted glass. Normally what they'll do when they're going to, is it like glass blowing videos, glass stretching, things like that? What they'll actually do is they will take quartz sand and melt it. And that's what that lava, they are actually making high silicon yield lava, okay? And then they're taking that with their special tools and they're stretching it and they're blowing it and they're doing all the things to it while it's still really hot and pliable, okay? Why do they use quartz? Does anyone remember what there's only 2 elements that go into making quartz? Anyone remember what it is? It's silicon dioxide. Silicon, 2 oxygens. That's all that we have to make our glass. The glass you see here is made through this process. Usually you melt some high quartz sand into a lava and then you shape it into whatever you want it to be and then you cool it off. And the temperatures that you allow it to cool it to, how quickly you cool it, whatever you add, maybe you add colors to it, that's going to dictate what type of glass you get out of it. Clear pane glass like this, stained glass, any number of different types of glasses come through this process. They are making it out of lava that they made by melting quartz, for the most part. Yes?
Would that mean like glass is like crystal basically?
Are you asking if it's like a mineral?
Well, yeah.
No. Who can tell me my definition of a mineral? It's a very important part of that.
Naturally occurring in organic solid that possesses an orderly crystalline structure, crystalline
Structure and a chemical formula.
and it can, yeah.
The glass we make has all of that except for one important thing, naturally occurring. We made it. Nature made this. We made that. So by my definition, at least, that's not a mineral. By some definitions, it might be. Just not by the purely geologic one. Okay? Good question. Yes, you may. Anything else? Okay. Now let's talk about the next thing you're going to need to know about igneous rocks, in particular, identifying them. Okay? textures. Igneous rocks have different textures. What does that mean? Igneous textures are determined by how quickly it cooled, what is the amount of silica present, and were there any dissolved gases that escaped while it was cooling off? Rate of cooling. We already kind of touched on this. What does that mean for the texture of my mineral? We talked about what happens when magma cools slowly and what happens when it cools quickly. What happens? Larger crystals when what happens? When it cools slower, larger crystals. When it cools quickly, smaller crystals. Bingo. This is part of our textural observation. The amount of silica, that's going to be very dependent. That's going to play a big factor in what minerals are there. Okay. And how far my lava flow made it, because it was either viscous or non-viscous. And then there's the dissolved gases. Because when you heat something up, you're going to release gases. When you cool something down, believe it or not, you will often still release gases. When you are entering different energy states, you're going to pull new elements into the process or release them. Or both. Both oftentimes are happening. Okay? When you take a lava and you quench it, you end up with your glass. Why? Why do you get glass? This looks like glass that somebody made. It is not. This is volcanic glass. How did we get that? From lava. Hold on. How did we get that from lava?
Quickly?
Yes, it was quenched quickly, but what does that mean? Yes, it was cooled down quickly. How quickly? Because we already established that if cooling is quick, you end up with a small crystal rock, right? A rock that has small crystals in it. How do we end up with that where there are no crystals? Oh, extremely quickly. This is what quenched means. Not just that it cooled down quickly, it cooled down almost instantaneously. The only bonds that had time to form, the silicon tetrahedrons. It made glass. Nothing else had time to form there. No, because if nothing formed bonds together, you would still have a liquid, right? The liquid is what you have when the bonds are too energetic to be connected. To go to another energy state, you have to remove that excess energy, which means that things are going to lock in place. What's locking in place here are the silicon tetrahedrons. Yeah. Yes?
Is silica absorbent?
Absorbent? Are you talking about the little silicon packs? Okay, so those silicon packs, they call them silicon. Silicon is one of the elements that goes into that. I don't remember the exact formula, but it is a highly porous, hydro-absorbent bond, okay? So it wants water to join it. You remember how we talked about how certain bonds pull other things into them preferentially? This is a silicon-based chain of chemicals that seeks water in the air to pull towards itself. So you'll see those little silicon packets that say do not swallow, right? There's a very particular reason why it says don't swallow. It's really going to mess you up on the inside if you do, okay? But it is actively pulling moisture out of the air. That's why they use them to decrease humidity for things like electronics and sensitive fabrics and things like that. Yeah. Okay, what else did you notice about this glass when it got passed around? You've already got it right now. Tell me what you see inside of it. Ah, there's bubbles. Why would there be bubbles inside of the glass? What did I mention about gases earlier? When you heat things up and cool things down, gases are often a byproduct. So why would there still be bubbles in this? It got hot and it cooled down how quick? Huh? Super rapidly. Almost instantaneously. No time for the gas bubbles to escape. So what you're seeing in there are bubbles of gas from when that cooled off. There is a whole group of different geologists that will go and find glass like that with preserved gas bubbles inside of it. They will drill tiny little needles through into those gas bubbles, capture that tiny little bit of gas, and then do a gas evaluation to determine what was going on in this lava flow at the time the obsidian was formed. It's pretty cool. All right. So now that we've gone through and we've explained this glass, let's talk about the igneous textures, okay? Your first texture you need to know, aphanitic. Aphanitic is the texture we use to describe small crystal-sized igneous rocks. Remind me again what the small crystal size would mean. Fast cooling. Not instantaneous, because there are, in fact, crystals. It's not obsidian, but fast. Okay? Very fine grained, very fine, tiny little crystal sizes, often microscopic. We will also often find the gas bubbles in these. Okay? This is another textural observation. We call that vesicular. Those bubbles, vesicles. The texture, vesicular. So if I were looking at this right here, I would describe it as an aphanitic, vesicular, extrusive igneous rock. What do those words mean? Extrusive, formed on and near the surface. Aphanitic, microscopic crystal size. Vesicular, filled with gas bubbles. If you say those descriptions to me, I immediately, in my head, can picture something that you might be looking at. You put that together with a composition description. Like looking at this right here, the color of this rock is a dead giveaway in a lot of ways. What composition would you say this probably has? Remember our compositions? Felsic, mafic, intermediate, ultramafic? What color do you observe in this rock? Very dark, which is a pretty good indicator that it's rich in what kind, what classification of silicates? Yes, dark silicates, meaning that this is a mafic rock. Bingo. And there are more tests that you'll do in lab to make sure of that, but just looking at this, pretty safe to guess, that is a mafic composition. So what's our total description of this rock? Extrusive, aphanitic, vesicular, mafic igneous rock. And with those four descriptions, I immediately in my head, as a geologist, knowing what all those words mean, can picture exactly what you're talking about. This is the power of observation. You're making these observations, writing them down, so that you know how to communicate about these things. Okay? All right. Now, something I want to point out here. This cross-section of a lava flow. Okay, so this was the bottom of the lava flow where it was flowing over the ground. This is the top of the lava flow where it was exposed to the atmosphere. Tell me what you observe about the degree of the number of vesicles, the vesicularization, if you want to use the fancy word, going through this cross-section. What do you observe? Yeah, there are not nearly as many vesicles down here. The number of vesicles and the size of the vesicles increase the higher up you go. Why would this have happened? Well, it's all cooling, but where is the highest degree of cooling? Nearer the outer surface of my flow. I am losing heat faster up here than I am down here. So while my gases are being generated down here, it is still non-viscous enough to allow the gas bubbles to travel upward until you reach the outside of the flow where it's cooling off too fast. They get trapped there, and boom, you end up with this. Okay? We following that logic? Kind of tying a couple of different ideas that we've talked about today together to answer a question about what we observe here. Okay? I like to call those logic trains, where you're just kind of like you start out with a few observations and you chain them together to end up with your result. Okay, we're going to be doing that a bit in this class. Okay, so there you go. That is aphanitic. Next texture, phaneritic. These are the large, easily visible crystal sizes. Meaning what about cooling? It cooled slower. Yeah, underground, definitely. More time for those crystals to form. They actually have coherent shape. They interlock with each other. This is an example of a felsic phaneritic rock, where you can see it's mostly light silicates with a few scattered darker ones in there. This is an example of a phaneritic felsic igneous rock. We can see it's clearly mostly dark silicates with a few scattered light silicates. And then this is an intermediate phaneritic rock, where it's an approximate 50-50 split between the two, light and dark silicates. Then we have one called porphyritic. Porphyritic. This one's a little tricky. Here's an example of it right here. I have both aphanitic texture, so tiny little microscopic crystals, and large, easily visible crystals. How could I get both? How is that possible? Not a rhetorical question. Throw out some ideas. What do we know about aphanitic and phaneritic textures? Yes?
This is about the crystals, right?
Yes.
Well, for the first one, it says that the crystals are only visible through a microscope because they were cooling rapidly.
Right, so we have rapid cooling to make the small crystals.
The second one was cooled slowly.
Slow cooling for the big crystals. Yes. So how might we get both in one rock?
Well, because it's inconsistent, so it's doing both. It's cooling slowly and fast.
How could that happen? Is that able to happen simultaneously?
I don't know. Could it?
Do you guys think it could happen simultaneously? Sure. Okay, we have a devil's advocate. Can't really happen simultaneously. Can you throw something in the microwave and in the freezer at the same time? Not really. But can you do one after the other? Yeah. So, sorry I stole your thunder there. Tell me how this would happen then.
I would say like tectonic plates, like they would move.
Okay, I'm not so much looking for a mechanism, like what's generating heat. I'm just asking about the process of making this. I love where your mind's at, though.
I don't know how to describe it.
I promise it's more basic than you think it has to be. Okay, we're talking about a sequence of events here, okay? For me to have the tiny little crystals, I clearly need to have cooled off quickly. For me to have the large crystals, I clearly needed to have cooled off slowly. Which one must have happened first? The big ones. I can't cool off quickly and then cool off slowly, but I can start cooling off slowly, make a few crystals, and then cool off the rest quickly, can't I? That's how you get porphyritic. Different minerals form at different temperatures. Remember that? That's going to be very relevant for later on in today's conversation, but I've already introduced the subject to you, okay? So what you see here is the large crystals form at a higher temperature. They had time to cool off and make large crystals, and then all of a sudden, something happened. Perhaps it was tectonics. Something happened that caused this magma, which was partially cooled, to get shoved up near the surface and cool the rest off very quickly. And there it is. Porphyritic. That's how you'll get this. Good job, everyone. Good working together on that. Okay. Then, of course, we have our glassy. There are various different forms that glassy textures, aka obsidian, can take. I already showed you this super clear greenish tinted one. Okay. Then there's this one. I think this is the only other one I have out. It is. I have a couple other varieties, but they're in the back. This is called mahogany obsidian. Why do we call it that? It's got that lovely black and red marbling to it. This is fantastic material for facades, for anything that you really don't care about putting weight on or getting damaged. Obsidian is not strong. It can be extremely sharp, though. The sharpest scalpels in the medical industry are made out of obsidian. They are able to carve tissue so cleanly that it doesn't even bleed. It has an edge so thin, it's only a few atoms thick if you manufacture it right. It's incredible. Okay. Obsidian, yes, sorry. Lots of different varieties of obsidian. When I'm passing around, that's the mahogany. Very commonly, you'll see like rainbow obsidian, fire obsidian comes up in some places. It's very cool. Snowflake obsidian, I have a bunch of this out back. I just don't have any up here. Snowflake obsidian is actually what happens when it's starting to break down. This is old obsidian that's starting to weather away, but it makes these lovely kind of white snowflakey sort of spots around itself. Now, there are a few crazy types as well. I lived in Hawaii for 3 years as a kid. So we would go visit some of the islands that had, were the one big island that had volcanic eruptions every now and then. You go to a beach shortly after a volcanic eruption, and you're going to see this stuff get washed up on the side of the beach. Okay? It's long, thin strands of glass. It's hair thin. They call this Pele's hair over there. Pele is the Hawaiian fire goddess. Okay? The goddess of creation, because they recognize the volcanoes spit lava into the sea, more land is made, so she's their fire goddess and goddess of creation, okay? But why do they call it Pele's hair? Because as the lava gets spat out over the ocean, okay, and it cools off very quick, a single drop of lava can get spread out into kind of a string shape, and it lands in the ocean and immediately cools off into that hair-thin strand of glass, and it washes up on the side of the ocean, and you can pick it up in bunches, and it'll crackle and split and break apart, just like glass would, but it's in hair-thin pieces. So it can take on some pretty wacky shapes. Now, there is another igneous texture called pyroclastic. Now, I told you something earlier, which I am going to walk back just the tiniest little bit. I told you that all igneous rocks come from the cooling of magmas and lavas, right? This is the exception. Pyroclastic textured rocks come from volcanic eruptions. They are not necessarily the result of cooling lava themselves. They are the result of another part of the igneous process, which is an erupting volcano. So pyroclastic rocks will be made out of the ash. It'll be made out of the cinders. It could even be made out of the shattered pieces of the volcano that got blasted apart and partially melted. Okay? But we will describe these as pyroclastic if we can tell that they are made from that ash, the cinders, or have some sort of proximity to a volcanic eruption. Okay? It is very common to confuse these with sedimentary rocks, which you will learn about in a few weeks. No, you'll learn about those next week, actually. We're on week 2. So you'll learn about those in week 3. Okay? But sedimentary rocks are made out of the weathered bits and pieces of old minerals. And these are made out of the broken, shattered pieces of minerals and rocks. Okay? Then we have pegmatitic. Pegmatitic is the last texture. These are very large crystal sizes. Pegmatites, which we will talk a little bit more about later, are the last stage in the cooling of a magma chamber. So any body of magma that's cooling off underground, The last little bit of magma that cools off is going to make a pegmatite with extremely large crystals. Okay, anything larger than 2 centimeters, we're going to call that a crystal large enough to have been in a pegmatite. So if you're looking at a rock that has all of its minerals or most of its minerals larger than 2 centimeters, you're looking at a pegmatite sample. This is a picture from the Nika mine in Mexico. These are selenite gypsum crystals, and for contrast, that is a person there in the mine standing next to those crystals. I have a picture somewhere of my uncle, my great uncle. He went to this mine. They closed it off to the public in the 90s when I was still a little kid. Otherwise, I would have a picture of myself in there already. But a lot of our most valuable gemstones and very, very valuable metals come from pegmatites for reasons I will explain shortly. Any questions about igneous textures? Mm-hmm. Like this mine? Well, mining exploration in general has to start at the surface. There are a couple of ways you can do it. You can go around the surface. You can do a ground survey where you're looking for, okay, we found these minerals here, these minerals here, these minerals here, these minerals here. The presence of these minerals probably indicates that there's something else or more of those minerals underneath. So they'll start drilling for it. You start drilling deep enough, eventually, sometimes, like in the case of this, you're going to drill through into that cave, realize what's going on in there. Unfortunately, that's exactly the sort of thing that happened. Okay, they had built a mine in this pegmatite, and they built a mine shaft into these caves. And that's what I found. It was like, oh, it's amazing. We're not going to mine this. No. We need to preserve this. It's a natural wonder. But unfortunately, the fact that they had already opened a path into those caves had done some damage. Because for these crystals to keep growing requires constant humidity. There has to be water in there, and that water constantly has to stay hot. The temperature in here is perpetually, I want to say it's like 110 degrees. Okay? That temperature plus all of the water keeps growing these minerals. By making that shaft into here, they allowed the humidity and temperature to escape. This cave cooled off, these crystals stopped growing. So the reason why they closed it off to the public, they sealed it back up. They're trying to encourage the growth of these crystals again. Trying to keep one of their natural wonders moving forward, or at least prevent any more damage from happening to them. Okay? Okay. Great question. Any other questions?
Do they find them like that, or do they dig and clean all around? Like
No, this is how they were found. This is how they were found. It's pretty fantastic. Okay, so taking all of these things together, how are you going to identify igneous rocks using the things I've taught you about? Okay, so we have everything from our composition to our texture to how quickly it cooled. All of these things, we can work together with all of these different factors. So you can make a very simple sort of, this is just an example. It's a little bit more than this, and there are more samples you'll need to know for the lab, but this is just an example of how you can draw some conclusions based on observations. If I'm looking at something that I know is mafic, and I can clearly see the crystals making it phaneritic, I'm probably looking at a gabbro. Okay? Same thing for if I'm looking at something that is aphanitic, and it's clearly made out of mostly light silicates, making it felsic, I'm probably looking at a rhyolite, so on and so forth. I'm going to introduce you to all of these different rocks that you will probably run into most commonly right now. Let's start with granite. Who has experience with granite? Granite countertops, right. That's a very common one. People love their granite countertops. Now, I cannot tell you how many home developers or construction people I've talked to who market a stone as granite, and it is definitely not granite. Innumerable times. People are like, hey, check out these new granite countertops. I'm so sorry, that's not granite. Right? I actually had to do that to my uncle once. He was like, dude, check this out. I built a new fire pit outside, got this granite on a sweet deal. I'm looking at it, I'm like, that's not granite, man. No wonder you got it at a sweet deal. So, you're going to learn a lot of things in my class, most of which are of scientific value. but you're also going to learn some very practical things in my class, one of which is how to never get ripped off by a countertop salesman. Okay? So let's talk about what granite actually is. Granite is a phaneritic, felsic, igneous rock. Here's a copy of it right here. So phaneritic, what does that mean? Crystal size is large enough to see with the naked eye. Boom, bingo, solid, got it. Felsic, what does felsic mean? Mostly light silicates, bingo. With a few dark silicates. What, when you're looking at this, do you observe? What do I have? Mostly light, mostly dark? Definitely mostly light. These salmon pinks and whites in there, feldspar, potassium feldspar. Cool. The gray, now I'm going to pass this around. I'm just going to show this to the camera real quick. Stay with me here, camera. There we go. Look at that. What you see there as gray are actually transparent and translucent. They're only appearing gray in the light. That's quartz. Light silicate. So when you exclude those grays and you look only at the dark minerals, there's not that many. Maybe somewhere between 5 and 10% in there. That's biotite mica. The only dark silicate present in that sample. Quartz is always going to be present in your granite. It's always going to have a very low percentage of dark silicates. It's always going to be mostly made out of feldspar, actually. Okay? Feldspar is the principal ingredient in most granites. These are some really key indicators for you to know I'm actually looking at a granite, not a fake. Okay? Now, if I take felsic composition, just like that granite, but I change it to an aphanitic texture, so instead of cooling off slowly like that granite did, it cooled off quickly, but still formed crystals, I get a rhyolite. This is rhyolite. Hold on, let me show the camera. Oh, camera, you're freaking out. Don't freak out. I'm right here. I was like looking at the ground. Okay, rhyolite. Kind of pinkish white. Most definitely, based on the coloration anyway, made out of light silicates. Yes?
Can granite be black? Like all black? Like not all black.
No,
No, it
it cannot. Did I just ruin your life a little bit?
can't.
Do you have that at home or something?
I have something that looks exactly like that, but in all black.
I think I have what you. I'll pass something around in a minute, and I'm going to ask you if it's that. Okay. All right. So here is rhyolite, felsic composition. But the crystals, at least most of the crystals, you'll see a few larger ones in here, but most of the crystals too small to see with the naked eye. Okay. Aphanitic texture. Then there's our obsidian. I already passed around the obsidian. I'm not going to pass it around again. You already got to see it. Okay. Very, very, very rapid cooling, quenching even. So the different colorations you get in there, like in the mahogany one that I passed around. This one. Where is that red banding coming from? Ions in here that didn't bond with the silicon tetrahedrons, but are still oxidizing red. Okay, that's where the red in this mahogany obsidian came from. The different colors come from whatever's trapped in there that never became part of that silicon tetrahedron bond to make another mineral. Then the last felsic mineral I'm going to talk about, pumice. You guys have probably heard about pumice before, right? How many of you have ever been to a spa? What do they give you to take dead skin off your feet? It's a pumice stone. Do you know that that's an actual rock? Do you know that it comes from lava? Yeah, that's what this is. What we have here, the best way that I can think of that I've ever been able to come up with to describe this, what's your favorite soda? Root beer. Me too. I don't drink soda very often, but when I do, it's root beer. let's say we have a root beer, okay? Got a nice bottle of, I don't know, my favorite brand of root beer is Frost Top. Can't really find it out here. It's mostly out east. But let's say I take that bottle of root beer and I perform the unthinkable. I am shaking it, okay? Never, ever. Why would you do that? For a demonstration, get this. What happens when I pop that lid off? What comes out? Huh? The soda comes out in what form? It's foam. Yes, which is the soda filled with the gases of carbonation. Okay, it's carbon dioxide. Okay, it's that soda with all the bubbles in it. When a volcano first pops its cork, what's the first thing that comes out? It's going to be gases, and those gases pushing some of the lava out extremely quickly. That lava is going to cool off extremely quickly, get quenched, and that's where you get pumice. When you have a very high silica content lava that gets pushed out very quickly, so it cools down like this, it's basically obsidian filled with so many holes of gases that most of its volume is air. I'm going to pass this around in a second. This is not going to weigh very much. Most of its volume is air, which is why it works great as an exfoliator, right? This is glass with thousands and thousands of razor sharp edges that can take off your skin. Okay? This is so dense, so not dense it will float on water. Pumice floats on water. Okay? Pass that around. There you go. Please do not exfoliate with my sample. All right. Yes, you may. I totally forgot to take attendance today. Someone remind me to do that at the end. All right. Moving on to intermediate. There it is. All right. Our intermediate composition, aphanitic texture rock is going to be called andesite. Andesite. Look at this. It's just kind of generally gray. Why would it be generally gray? Because it's approximately equal proportions of dark silicates and light silicates. Your eyes are interpreting that as a generally gray color. Okay? Anyone want to take a guess as to where the rock andesite was first characterized and studied? It's in the name. The Andes. The Andes are made up out of a lot of this stuff, hence the name andesite. Okay? Next up, we've got the phaneritic intermediate right here. This is called diorite. Okay? Some people call it a salt and pepper rock for obvious reasons, but, huh? Nothing? Okay. But its actual name is diorite. Okay? Diorite. So, phaneritic, you can clearly see the minerals. What are these minerals? Amphiboles and sodium feldspar in this particular one. Okay? Equal proportions, dark and light. Moving on to our mafic category, basalts. Basalt's going to come up a lot in this class. Basalt is the most common extrusive igneous rock on our planet. It is mafic. It cools quickly. Which of our two types of crust on the surface, continental or oceanic, is mafic in composition? Bless you.
Thank you.
Is the continental crust mostly mafic, or is the oceanic crust mostly mafic? Oceanic. Thank you. It is thinner. It is mafic. It covers, how much of our surface is covered in water? 71%. Most of our planet's crust is in fact mafic. That is why basalt is the most common extrusive igneous rock, because this is what makes most of the oceanic crust. Okay? So here we have something that's clearly made out of mostly ferromagnesian minerals, dark silicates, right? Your olivines, your pyroxenes, your amphiboles, your biotite micas, all of that. Okay? Basalt. Very, very common. That's basalt, B-A-S-A-L-T. Okay? Now, when you take that mafic composition, but instead of putting it out at the surface quickly to cool off, you let it cool down slower, you get the phaneritic version called gabbro. And I think this might be Jordan I think this might be what you were talking about. Does it look like that?
Kind of, but like it has white. Well, it's probably just like the rock, but it has white inside of it, like little chunks of white.
Little chunks of white? Are they glittery?
Some are, some aren't.
Some are.
Yeah, I guess so.
Okay, so it's like this, but with little pieces of white in it?
Mm-hmm.
It might be synthetic stone. You don't really find that degree of contrast. If you want to bring a picture, though,
Okay.
yeah, I can work with a picture. Okay. Most of the time, gabbro will be cut like this. This is a piece of gabbro countertop. Sorry, let me get my camera back on me here. This is a piece of gabbro countertop that someone bought thinking that it was granite. It's not going to have the same quality as granite does. Why? What does granite have that gabbro cannot as a mafic rock? What is a principal ingredient in granite that gabbro cannot have? Yes, it is one of those. Huh? No, so felsic is the composition of granite, but there is something in the felsic composition of granite that this being mafic cannot have. Quartz. Quartz. You may not have made it far enough in your lab to know this yet. On our Mohs scale of hardness, which goes 1 to 10, quartz lands at a 7. Quartz is harder than most other minerals that are easily accessible, making it a fantastic worktop. Why we love it for granite countertops. Granite has quartz in it. Gabbro doesn't. Gabbro is made out of softer minerals that hang out around the 5.5 to 6 range. Okay? But this still gets marketed as granite a lot of the time because people will just say, oh, it's a rock, let's call it granite. Okay? Don't get suckered in. You know better now. Okay? So, gabbro, phaneritic, mafic. Roughly the same composition as that basalt, just took longer to cool. So that's why we have these larger crystal sizes. All right, now we're going to talk about some pyroclastic textures. Pyroclastic. When you have volcanic ash that gets blasted out of a volcanic eruption, goes through the atmosphere, and then lands again, it is usually still very hot. So hot that it will weld together. The little bits and pieces of ash, which, by the way, ash is just glass. Okay? It's just pieces of glass, microscopic pieces of glass that are falling like snow. They will weld together because they're still so hot, and that gives you something called a welded tuff. And here's what that looks like. You're going to see little glittery pieces in here as I pass this around. Those are other pieces of debris from the volcanic eruption. Come on now. Stick with me. Other pieces of debris from the volcanic eruption that got pulled in and welded inside of this with the ash. But the main body of this rock is nothing but volcanic ash that welded together. When that same process happens, but you have a much larger percentage of debris, like volcanic shrapnel, pieces of just shattered rocks that get incorporated in the ash, we call that a volcanic breccia. That's what that word is right there, by the way. B-R-C-C-I-A, breccia. Volcanic breccia. You can see it still has some ash in there binding everything together, but there's much, much more debris in here. Okay? Okay. Any questions about volcanic textures, or igneous textures, I should say? All right, so now let's talk about where this magma comes from in the first place to start this whole process. We talked about this. Contrary to popular belief, it is not completely melted underneath the crust. We're not bumper boats on an ocean of magma. It is solid down there. So how do we end up with melted stuff at the surface? Hot stuff rising from near the outer core, sure. But that can't explain every scenario for where a volcano forms. So then how do we get it? There's this thing called the geothermal gradient. Okay? This is the Tautona mine in South Africa. It's the deepest mine in the world. Last I checked, anyway. Look at that. Isn't that incredible? That massive hole in the ground. This is a figure from 2015. So I haven't updated it in a while. But in 2015, this was a 2.5 mile deep mine. It is so hot down there that anyone that goes down there has to spend time in a refrigerator at regular intervals or they die of heat stroke. They build little refrigerators down there specifically so that their workers won't die. Okay? This is one of the primary locations in the world where they are working really hard to try and figure out robotic workers so that they can take human safety out of the equation. Okay? It's a gold mine that brings up so much gold that it is still worthwhile to keep digging deeper. Okay? Why is it so hot down there? Huh? You're still pretty far from the core, but you're 2.5 miles closer to it. Yeah. The deeper you go underground, the hotter it gets. This is called the geothermal gradient. Okay, so here's a very simple, easy to read 3-axis diagram that explains it. Don't worry, I'm going to explain it. Okay, I need a good pen, though. Oh, I forgot I took them all out. Okay, here we go. So, on this axis, pressure. On this axis, depth. This axis, temperature. 3 curves you need to know. Well, really 2 that matter. This pink line right here is the melting point of the mantle rock. This crimson line is the geothermal gradient, which is the rate at which temperature increases the deeper you go underground. It's not constant. It's not a linear line. It's a hockey stick. It flattens out at one point. Right here, at about 1500 degrees Celsius, at a certain point right there, it's going to flatten out. It's going to make this hockey stick shape. Notice, here, by default, under normal circumstances, does my geothermal gradient and my melting point of the mantle, does it ever touch? Ivani, what do you think? My geothermal gradient and my melting point, under normal circumstances, do they ever touch? No, look, they get so close, but they never actually touch. Okay? Because as the pressure is increasing, my temperature increases less. Now, something has to happen for these two lines to cross and us to have melted mantle rock. One of three things has to happen. The first one is increased temperature. What happens if I increase my temperature? What direction, on what axis does my geothermal gradient move? My x-axis, right? It's going to shift this way, increasing temperature. If I increase my temperature at a certain depth, boom, the lines have crossed. I now have melted rock. What can cause that increase in temperature? Usually tectonics. Plates colliding with each other or scraping past each other can cause this to happen. Okay, that's the first way. We increase temperature. What's the other way, or another way? We can decrease pressure, right? If I am at this temperature, if I am a rock at this temperature and that depth, but I decrease my pressure, what am I doing? I am shifting up on the pressure scale. Okay, right there. Decrease temperature or pressure usually by approaching the surface. I am maintaining the same temperature, but coming closer to the surface, removing pressure, boom, bada boom, I have passed that melting point and I can have melted rock. Where can this happen? Well, let's say that I'm at an ocean ridge, okay? There's the ocean bottom, right where two plates are splitting apart from each other. This zone right there between those two plates, up near the surface, is the lowest pressure zone in the area. So any mantle rock that gets pushed up there goes through this. Decrease pressure, maintain temperature, I get a pocket of melted magma there. And that is where new ocean crust gets spat out and added to both sides of this rift. That's our second way. The third way, we change the chemistry. What does that mean? I'm going to say something here, and y'all might look at me like I'm crazy, but just bear with me, okay? Water. We think of water as being like the antithesis to heat, right? We use water to make things less hot. That's a physical property. That water is smothering the heat, absorbing it effectively. If I dumped a thimbleful of water on a hot cooktop, it would evaporate away. It can't absorb all that heat. If I dumped a 5-gallon bucket on top of a hot cooktop, it will absorb that heat, disperse it, and my cooktop won't be hot anymore. It is the quantity of water that controls the heat that you're applying it to. That's a physical property, not a chemical one. Get this. When you add water to rock, it lowers the melting point of rock. That's a chemical attribute. Chemically speaking, the minute that you introduce water to the chemistry of a rock, it drops the melting point. Okay, so what does that do here? If this pink line is my melting point for mantle rock, and I introduce water to it, it shifts the whole thing where? Left. So now my melting point is like this. My lines cross again. I get melted rock underground. So under what circumstances does that happen? All right, let's go back to our ocean crust. Here is my ocean crust, except now something has changed. I am subducting. Let's use a different color for my continental plate here. I am subducting under a much thicker continental plate. Convergent plate boundary between an ocean plate and a continental plate, right? Subducting, shoving underneath. Great. No, pen, no. Fantastic. I have my two plates, but what does this do? Do I not have any blue pens? I guess purple will have to work. All right. What is sitting above that oceanic plate? Water. The ocean, right? So the ocean is above here. Not only is it above there, water has percolated, invaded the top at least several hundred feet, if not more, of the ocean crust. And you know where that water goes? It gets carried underground right there alongside that ocean crust. The deeper this ocean crust gets shoved under this plate boundary, the more it gets heated up in the mantle. What's going to happen to my water? What happens to my water when I heat it up? Huh? It boils and turns to steam. Steam does what? It rises. Why does it rise? It decreases its density. So as this water heats up, it's going to decrease its density. So it's going to start making its way up through this mantle rock underneath the crust. What's it going to do to the mantle rock under the crust? Lower the melting point, which allows us now, red pen time. We're going to get pockets of magma in my mantle right there. Where's that magma going to go now that it is not as dense as the rock around it? Up. It's going to chew its way up here. And that's where we're going to get volcanic eruptions. This is where you get your coastal mountain ranges. The Andes, the Cascades, parts of the Rockies. Okay? Any mountain range, you look at these maps around this room, you look at any of these mountain ranges along the coastline, that's what's happening here. Volcanic mountain ranges because of this process. Water melting or water causing the melting point of the mantle to drop as it's introduced there. Isn't that crazy? Okay, those are the three ways that we can end up with melted mantle, which is magma now, which can cause or feed these volcanic igneous processes. How do we feel about all that? Do I need to dive any more on any one of those? Pretty good with it? Leilani, you following along okay? Good. Okay. And that one right there. Okay. So, that leads me to the next component here. If magma is formed deep underground through one of those three processes, in all of those three processes, what was it? What layer of earth was it that was melting to make the mantle? Or, I just gave it away. To make the magma. It was the mantle, right? Little slip of the tongue there. We are melting mantle rock to make that magma. What is the composition of the mantle? Is it felsic, intermediate, mafic, ultramafic? It's not intermediate. Remember, the crust is high in those light silicate minerals. The mantle, not so much. Huh? Sorry, I can't hear. What? No. What do we call the composition that has extremely little to zero light silicate content? Someone take a risk, gamble. I promise I'm nice. I won't be mean if you're wrong. Mafic is high in dark silicates, but still has the presence of some light silicates. We need something more extreme than that. Something bigger, better, something more ultra. Ultramafic, there it is. Yes, the composition of the mantle is ultramafic. Okay, so if we're melting the mantle, which is ultramafic, to make magma, which therefore must be ultramafic as well, that's where we start. For the longest time, people thought that whatever the composition of the rock that melted was, that's the composition of lava that would come out of the eruption. But this guy in the 19th century, N.L. Bowen was his name, he did some experiments. He melted rock and then kind of cooled it off slowly and watched what happened. What he found was that the composition of magma changes over time. And this gave us something called Bowen's reaction series. Okay? So there is crystallization that happens as minerals are forming. And as minerals form, the composition of the remaining magma will change. So for example, we have right here at the very tippity top, 1200 degrees Celsius magma, freshly melted mantle, ultramafic composition. I'm going to start forming olivines as it begins to cool off. What are olivines made out of? Sure, silicons and oxygens, but there's plenty of that to go around. Iron and magnesium, though. Every single olivine bond pulls an iron and a magnesium out of my magma to make a crystal. And you get billions of those to make a bigger crystal. And then you make billions and trillions of those crystals. Eventually, you're going to end up with a magma that does not have as much iron and magnesium as it did before. And what does that do to the composition? It changes it. No longer are we looking at a purely ultramafic magma. We're looking at a mafic magma because the ratio of silicons to iron and magnesium has shifted a little. Okay? So, next up we form our pyroxenes, and we start forming some calcium-rich feldspars, and then we form some amphiboles. By the time we reach a certain temperature threshold where all of those things have been forming, we have pulled even more irons and magnesiums out. And now we're no longer even looking at a mafic magma, it's more intermediate. Then we start forming our biotites and our sodium-rich feldspars and all of that. And we cross that boundary into the remaining magma being felsic. And then we start forming all of our other feldspars and our muscovites and our quartz right at the end. So what did this prove? No, there are not distinct starting characteristics of a magma chamber that dictate what it's going to look like for its whole life. It's not going to be a felsic magma chamber for its whole life. We know they all start ultramafic and they all end felsic. Okay? So now is when we get to hand out those M&Ms. So everyone's going to get a bowl of M&Ms. And for those of you watching this online, I'm sorry you don't get M&Ms, but you can follow along using the thing I'm going to put up on the screen here in a minute. Everyone gets a sheet of paper. This is your very own magma chamber. Woohoo! Okay. I think I have enough for everyone today. There you go. Yeah. Yeah. Oh, I need to leave one over there. She stepped out for a second. There you go. Right there. All right. Yeah, just barely enough. All right, now everyone is going to get a bowl of M&Ms. Now you'll notice at the bottom of your paper, there is a key that tells you what color of M&Ms. Please don't eat any yet, by the way. You can eat them after we're done with the exercise, just not yet. They tell you, that key tells you what color of element each M&M represents. Okay? What? We are going to be building these bonds, these chemical bonds, one by one, and seeing how the overall chemistry of your magma chamber changes. Did I miss anyone? We still have 2 bowls here. I think there's only 13 of us here today. Doesn't matter. All right. So, camera is going wild. Right here. This way. This way. Hey. Make me unplug you. There we go. No. Right here. Right here. There we go. Here we are. Okay. Moving on. All right, this is Professor Hart's M&M differentiation sequence. We are going to be replicating the Bowen reaction series using M&Ms, okay? The first bonds that form right at the top, right at the highest temperature, is going to be olivine. So you're going to take 2 purple M&Ms, and it should be an orange. Orange represents silica, by the way, silicon. Okay, so irons are green. Magnesiums are purple. Iron and magnesium, remember, are interchangeable in olivines, so you can use 2 greens, a green and a purple, whatever the case may be for this. Silicons are orange. Aluminums are blue. Calciums are yellow. Potassiums are red. And then you have a category of other, which we'll come back to in a little bit, called brown. Oxygens are implied. Okay, if I were to include oxygens in this exercise, you would have about 500 oxygen M&Ms in each bowl, so we're not doing that. Okay. Oxygens are implied. So you've made your olivines. Go ahead and drop it down here to the bottom because they are the first things that form in my magma chamber. Where are they going to settle out? The bottom. Gravity is going to do its thing. They're going to filter down to the bottom here. Okay? But they have removed iron and magnesium from the equation. You used to have a certain number of irons and magnesiums in your magma chamber. Now you have less. The ratio has shifted. Okay, now we're going to make pyroxene. Okay, so you're going to take an iron and 2 silicons. Silicons are orange. I know, the projector kind of turns the orange into yellow over here. Okay, and those are going to go down here just above olivines because they're sitting on top of them. Okay. We've pulled even more irons and magnesiums out. We are no longer in what can be described as a purely ultramafic environment. Okay. Next up, we're going to make amphibole. Yeah, things are getting a little more complicated here, okay? 5 irons, 2, 4, 6, 8 oxygens, and 2 calciums should be yellow. Yes, they are. Oh, that's 8. Yep, 5 irons, 5 green. All right, now we're really depleted in our irons, aren't we? We can't really say that we are working in a purely mafic environment anymore either because the ratio of irons and magnesiums has dropped substantially. So we're going to shove these amphiboles down here. And we're going to make some calcium feldspar. 2 aluminums, 2 silicons, 1 calcium. I put a little black outline around the calciums because it was hard to tell apart from the silicons. We have moved solidly into the light silicate formation phase, okay? Now we're going to make potassium feldspar. 3 silicons, an aluminum, and a potassium. Not only is your magma chamber becoming depleted in anything, right? So much of its mass has turned solid, it's also becoming depleted in the things that were formed first. Let's take a quick inventory. What do we have mostly left in our magma chambers now? Yes, that's your magma chamber. Sorry. The bowl of the M&Ms was your magma chamber. We have a lot of orange, right? We're becoming even higher and higher concentrated in silicon. Our ratio of irons to magnesium and silicon has now gone the other direction, right? There's still a few irons and magnesiums left. Okay, potassium feldspar has shifted. Now we're making biotite. 3 magnesiums, 3 silicons, an aluminum, and a potassium. The last dark silicate that we can make. Those are going to get shifted right down here. And then we're going to make another doozy. Muscovite mica. 6 oxygens, 2 aluminums, 2 potassiums. We're coming up on the end, folks. There's not a whole lot left to work with in our magma chamber, is there? We've spent millions of years making all of these other minerals. Look, my corn syrup is almost all flowed down to the bottom here. It'll take about 2 weeks for everything in here to make its way down there. Six oxygens, 2 aluminums, 2 potassiums. Not a whole lot left, is there? There's just one mineral left that we need to form. The thing that forms right at the end, it's very common in felsic rocks though, quartz. Just one silicon. It's SiO2 and the oxygens are implied, right? Just that one silicon. Okay, what's left? What do we have left? You got a couple oxygens, couple aluminums, couple potassiums, couple calciums, 1 magnesium, but notably, you had 2 brown M&Ms in there. What does brown represent on our key? Other. Now, those 2 M&Ms initially in our first ultramafic phase were 2 out of, what, 100? You maybe didn't even notice that they were in there, some of you. Negligible. Now we're at the end. The ratio of other to everything else, much, much higher. Our magma chamber is at the end of its life cycle. It's almost completely cooled off. Almost everything is solid. Almost everything is filled in. What do we have left? Just the dregs at the end. That other category, okay? That other category up there, go ahead and put your 2 browns up there. Those are the elements that do not typically want to bond to anything. But now we are at such low temperatures, and I guess you could say they don't really get to pick where they go anymore. They just start forming minerals. Those other elements are the really, really rare ones, like our rare earth elements I talked about last week. They form in the pegmatites, right at the end of the magma chamber cycle, which is why, like I mentioned last week, pegmatites make for extremely valuable mining targets. Those other elements are finally forced to take solid form here. Okay? So that's just kind of your breakdown of a magma chamber's life cycle. Does that make sense? The M&Ms help you visualize all of this happening, pulling stuff out of your magma chamber, changing the composition of your magma chamber over time. All right, good. Then you may proceed to eat your magma. All right. While you're doing that, I'm going to explain to you how this linear progression of chemistry change in your magma chamber can be tweaked, can be messed with a little bit, okay? So this is what it normally looks like. We have our fresh, brand new magma body, cools off over time. There is crystal settling. our magma chamber is not only cooling off, it's changing its chemistry. And then right there at the end, instead of having our mafic body up here, we've got our felsic body down here. But a few things can happen to mess with that. Assimilation is one of them. Assimilation is essentially, well, let me put it this way. As my magma chamber is chewing its way up through the crust from the mantle to get up to the surface, do you think it's just saying, excuse me, make way please, I'm coming through? No, I've never met a magma chamber that polite. What are they doing instead? Yes, they are melting its way through the rock. It's chewing its way, literally assimilating everything in the rock that it's melting through into itself. So while I start off ultramafic on my journey up through the crust, depending on which kind of crust I'm going through, I'm going to either speed up or delay Bowen's reaction series as a consequence. If I am an ultramafic magma chamber chewing my way up through a continental crust, which is mostly felsic, I'm going to be incorporating more felsic materials into myself, therefore speeding up Bowen's reaction series. I get felsic compositions faster than I would have otherwise because I'm incorporating previous felsic rock into myself. If I am chewing up through a ocean crust is mostly what composition? It's the general composition of ocean crust. If continental crust is mostly felsic, ocean crust must be Mia, what do you think? Continental crust mostly felsic, ocean crust mostly You could. I just did. Continental crust mostly felsic. Ocean crust mostly. Continental crust is mostly felsic. It's mafic, yeah. Ocean crust is mostly mafic. Okay? Dark silicates, right? Thin, dense. Remember that. This is an easy way to remember. Ocean crust is thinner and denser than continental crust. Why is it thinner and denser? Because it's made out of those dark silicates that are mostly iron and magnesium. Okay? Mafic composition. Okay? So if I'm an ultramafic magma chamber chewing my way up through a thinner, already mafic ocean crust, my chemistry is not really going to change. So I'm going to go through the whole Bowen's reaction series there under that crust. But if I'm chewing my way up through a continental crust, I'm going to assimilate a bunch of stuff into myself. Okay? So that's assimilation. Then there is magma mixing. Let's say I have an old magma chamber coming up through here, okay? It's, say, halfway through Bowen's reaction series. Maybe it's at an intermediate phase right here. But then another newer magma chamber comes up underneath of it and slides right in, so they become one magma chamber. I take that fresh new ultramafic material, I mix it with that intermediate material, all of a sudden I'm back to mafic, right? They're going to mix and find somewhere in between. So these are a few ways that we can kind of reset or jump ahead in Bowen's reaction series, depending on what else happens along the way. Okay? Now, I want to talk about partial melting. You have learned already that each mineral has unique sets of properties that we use to identify them. We already talked a little bit today about how certain minerals have different crystallization points. Okay? It's like in that porphyritic rock. One mineral started to crystallize earlier on and made large crystals before the rest of it got shoved up to the surface and all of it cooled off, right? Those were different crystallization phases. Those are the same as melting phases, okay? Partial melting. So what we have here is 3 different materials: linseed oil, water ice, and chocolate. As you start to raise the temperature here, you're going to notice that the linseed oil starts to melt first, while the other two do not. So if I have a rock that starts to melt, but not all the way melt, we call it partial melting. Okay, as we go over here to 0, my ice is going to start melting. Boom, there it is. My chocolate is still a solid. If I was treating this like a rock and I just stopped it right here, I would have magma made out of the melted remains of the oil in the water and solid chunks of chocolate. Same thing in magma. If I take a rock like granite and I heat it up, I'm going to first melt my quartz, because it's the last thing to form in Bowen's reaction series. Then I'm going to melt my feldspar and muscovite mica, because they were the other things to form right before quartz. But if I have, say, any amphibole in there, I'm going to get a soup made out of the first 3 minerals with chunks of amphibole floating around in it. That's where you have solid phases in your magma. And that's what gets you things like porphyritic textures. Okay, so continuing along here, my water ice is fully melting slowly. We're going to keep pushing along, and eventually my chocolate, I pushed play. Hello? Hello? It didn't like that I paused it. Hold on. Okay, we're going through the progression. We're going to start melting our ice right now. Okay, it's going to pause there for a second. Then it's going to keep pushing forward, and as it does so, we're going to start melting our chocolate. And that is when we have a fully melted magma. Okay? So right about now, yeah, look, our chocolate is melting. Now we are full-on magma, all liquid phase, no solid phases left. Okay? That is partial melting. Okay, so these bodies of magma underground, I have referred to them as magma chambers. Kind of a generalization. We have names for all the different types of magma chambers. Okay, we call them these certain names based upon a few characteristics, namely their size and orientation. Okay, so for example, a pluton is what we would refer to as any intrusive body. An intrusive body is just any body of magma that has come up into rock that it was not in before. It is intruding there, okay? We would call those plutons. So that covers kind of everything. We give them other names based upon shape and their orientation to host rock. Their shape can be either massive, like these, right, where they're just kind of blobs, or tabular, where they kind of form a sheet that either cuts through or across rock. The rock that was there before. And that's where the orientation comes in. Discordant means that it is slicing through the layers of rock that were there already, perpendicular to them. Concordant means that they are slicing parallel to those previous layers of rock. Okay? Or parallel, I already said parallel to those layers of rock. Okay? Let's talk about a few examples here. Tabular bodies, intrusive tabular bodies that slice perpendicular or discordantly to the layers of rock are called dikes. Okay? A dike cuts across the layers of rock. And this is an example of one right here. You can see it's slicing vertically through layers of rock that were there already. Okay? Then there are sills. A sill like this is Giant's Causeway over in Britain. I highly recommend going to visit if you haven't been over there. It's fantastic. But these are layers of rock, or excuse me, layers of magma that sliced parallel to the layers of rock that were there already. Now, I really need to drive this home so that there's no confusion. Perpendicular and parallel, not vertical and horizontal. Here's the big difference, okay? If I have layers of rock that were here already, like so, there's 3 layers of rock, and I have a dike that slices whoop, like that. It is vertical, no? True. Yeah, absolutely. And I have a sill that goes whoop. That is horizontal, correct? Is my dike perpendicular to the direction of the rock that was there already? Is this perpendicular to those layers of rock? Yes, it is. Good. Is this one parallel to those layers of rock? Yes, it is. Good. So we have a dike and a sill, legally, right there. Okay? Now let's say my layers, let's say my original layers of rock have been tilted by tectonics to be horizontal, which does, in fact, happen. Okay? Now I have the same thing happen, where I have whoop, whoop. Which one's now my dike? This one is now perpendicular to them, even though it's horizontal. And this one, which is now my sill, is parallel to them, even though it's vertical. So do not use vertical and horizontal to describe dikes and sills. Use perpendicular and parallel with the original layers of rock as your point of reference. You following that? Great. Great, 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 great. Okay. All right. Now, the massive ones, okay? There are 2 different types, or 3, I guess, but one is kind of a subcategory. Okay, so you have batholith. A batholith is a massive pluton that is more than 100 square kilometers at its surface expression, okay? So a batholith is going to be, a lot of the mountain ranges out west are batholiths, okay? They form the core of a lot of mountain ranges because the igneous rock that forms from the magma underground that becomes the batholith at the surface is very resistant to weathering, more resistant than the weathering of the materials that were already at the surface. So they tend to stand out and make mountains, okay? When you have the next size down, which is it's just like a batholith but smaller than 100 square kilometers, you get a stalk, okay? Now that stalk and these batholiths, they're going to be sending out dikes and sills all over the place. See, here's a dike, but there's a sill. Here's a dike, but here's a sill. There's a dike, right? And sometimes these things, they shoot off in these different directions, and this magma starts pooling in other places. It pushes out of the stalk or the batholith, goes along one of these chutes, and then starts pooling somewhere. And as it starts to pool, it shoves the layers of rock above it upward. We call that a laccolith. Okay, so a laccolith is a pool of magma that grows underground, okay, and it shoves the layers of rock above it up instead of just cutting through them like the stalk and the batholith did. Right. So, quick note about mining in pegmatites. A lot of the more important mining targets are coming out of pegmatites. It's where you get things like your rare earth elements, lithium. Who can tell me what we use lithium for these days? Batteries. Bingo. Lithium-ion batteries are huge. Rechargeable batteries. Okay? More and more, we need lithium. And lithium is getting harder and harder to find because a lot of the easy stuff has been found already. Okay? We're needing to do lots of inventive things. There are 2 companies here that are setting up in the Permian Basin right now. Their entire profit line is taking all the wastewater from the oil wells, which I don't know if you guys are familiar with this in the oil industry or not, but wastewater coming out of wells is a big problem. Where do we put it? Where do we keep it? It's useless. We can't do anything with it. These people are taking all that wastewater and they're evaporating the water away to get the elements out of what's left. Turns out our wastewater here in the Permian Basin has about 10 times the value of wastewater, of 10 times the value in lithium that wastewater almost anywhere else does. So they are going to make a profit scraping lithium out of our oil-filled wastewater here. Yeah?
Why is there so much in the Permian Basin?
It just has to do with what's in the layers of rock thousands of feet underground that the oil is in. The oil is coming out of layers of rock, but so is a lot of water, right? We use a lot of water for fracking the wells, and there's a lot of water that comes up with the oil as well that we have to separate out, okay? And then we take all that and we stick it in a tank because it's waste and we don't know what to do with it. It would cost too much money to clean it and use it again, so we just put it in tanks and have it sitting around. Well, now there are people that want to extract the trace minerals inside of that water, which is fantastic because they're evaporating that water away. Evaporating that water purifies the water. They siphon that off. Yes, that is something we can use again. It's incredible. And I hope that more companies get into realizing there are probably some minerals in this water that we could utilize, not just the lithium. There's a bunch of other stuff in there as well. But that's just an example, okay? So the minerals that come out of these pegmatites, very valuable. Another thing that comes out of these is what's called hydrothermal solutions. So right there at the end of this magma chamber's life cycle, when all of these last few minerals are forming, the local groundwater is going to start seeping in there. That's what made all of those crystals, that big cave and that Nika mine. I mentioned that it needed to be constantly wet for them to keep growing. That's local groundwater that seeps into the system, gets superheated, and all of the dissolved minerals in that water make those crystals. We call that a hydrothermal solution. Well, sometimes those minerals get carried away by the groundwater. My job at the gold mine I used to work at, I was an exploration geologist at a gold mine in Nevada, was there were these Jurassic age plutons that at the very end of their life cycle, groundwater came in and stripped away a whole bunch of valuable metals, gold, silver, lithium, whole bunch of stuff. Stripped it away and carried it through the groundwater system for miles and miles before cooling off enough for those minerals to form actual crystals. Things like gold and silver and lithium deposits and all of these things, uranium, okay? All of this got carried away by the water. My job was directing drilling teams, and we were just drilling holes. We would drill holes 500 feet, 500 feet, 500 feet, 400 feet, 300 feet here, 200 feet, 500 feet again. We would drill down following the path that this groundwater took millions of years ago through the layers of rock. Following the traces left behind of this gold. Okay, there's a little bit here, there's a little bit here. Oh, we lost it. Okay, let's come back this way. Maybe it went that way. We found it again. We're following this path until we find where it ended up. Boom. We just hit a pocket of high concentration gold ore. We tell the mine, they buy the land, right? We would need to, usually you would buy permission to explore there or buy the land outright if you suspect it's there and then explore there. Boom, we know it's here. We drill this entire area just to make sure we know the boundaries of what we're looking at for the economical extraction. And then we tell the mine, okay, this is your boundary. Board of trustees or whoever is in charge of making the big financial decisions, okay, in the next 5 years, we're going to invest $25 million in this new pit. Okay? 5 years later, after all the infrastructure is established, they start digging. 5 years after that, they start making a profit on it. It's a very long process for mining these days before you start getting a profit on. It's a huge investment up front with a big profit over decades afterward. It does pay off in the end, but it's a lot of upfront cost. But that was what I did. Following these geothermal deposits, these hydrothermal deposits of precious metals to where they ended up because of this process from these pegmatites. Okay. Any questions about intrusive activity? No? Okay. Well, I went a little longer than I thought. I waxed a little bit enthusiastic at parts, I think. We still have about 30 minutes left in class, so feel free to work on lab. There were questions about lab, right? Yes? Questions about lab? Chloe, I thought you had a question. No? Are you struggling at all in the lab, or you feel like you've got a grasp on it? An idea of what you're doing. Okay. Well, let's use the next 25 minutes here to do what we can on it. All right? I'm going to end the recording here, and we can jump into lab time.